Hello, everyone. Welcome to the Neural Implant Podcast. Today's guest is Dr. Ulrich Hofmann, and he is from the University of Freiburg in Germany. You may recognize the school from some of our previous guests, such as Thomas Stieglitz a few episodes ago, and then Dr. Maria Asplund all the way back at the very beginning of the show. So he's joined by good company, and he is kind of, I guess, a polymath. He's done a lot of different things throughout his career in the field of brain-computer interfaces. Started out in silicon, then went to soft devices. Now he was doing kind of a genomics, transcriptomics, and now he wants to do like nanoparticle sensing and recording of recording and stimulation of neurons. So very interesting. He's German, so he's very direct, and he tells you exactly what he thinks. And I love this. I love this kind of trait. So really enjoyed this. Dr. Ulrich Hofmann, pleasure to have you on the show. You are the professor, you're a professor in the Department of Neurosurgery, I think, right? Uni Freiburg in Germany. We've had a few of your colleagues on the show already, Dr. Thomas Stieglitz and Maria Asplund. Honestly, I have to say, Freiburg is the most beautiful city in Germany. I very much enjoy it. I very much love it. But you don't live there, and I think we'll probably get into it. But pleasure to have you on the show.
Yeah, thanks for having me here. I mean, I'm following your podcast slightly, not really intensely, but recently, due to this interview, I listened to more of your programs. And yeah, it's interesting what other people say. It's a little replacement for me to the missing conferences. Yeah. You hear insight from somebody kind of not showing off his pets and ponies, right? Just talking about things. That's what I'm really missing that. This is something that you had on conferences over a glass of beer or a tea, whatever. And and so a little more informal stuff. So I really like that. I'm happy that I found that meanwhile, and I'm listening to that too.
Yeah, exactly. Thank you. I mean, that is the intention is to, kind of keep things, keep people updated with what's going on. And actually, I mean, I don't know if you know this, you're one of the first people, you were the first person I went to talk to when I was thinking about putting together the podcast, what was it, 4 years ago. And yeah. I visited you in Freiburg and you gave me a great list of people that I could reach out to and everything like this. So you're responsible.
I do recall that. Now the question is, why did it take you 4 years to come back to me and then start a podcast with me now, huh? What does it mean?
I reached out like 3 times, and you're just like, oh, not a good time. So I think I must have caught you at a good time. Maybe you ate some ice cream and you're happy. And
probably, yeah.
But anyways,
science is a lot of psychology. If we are happy, then we are happy to share. If we are sad, then it's better to leave us alone.
I think so. But do you want to? So first of all, you're working in Freiburg, which is bottom, so southwest corner of Germany. But yes. I actually just found out that you don't live there. Where do you live?
I live in Lübeck, which is actually the northeast area of Germany. It's even north of Hamburg. And my colleagues and my students in Freiburg always ask me whether we have already polar bears around the corner. So it's that far up in the north, but of course we don't have that. It's too far from Polar Circle. But yeah, I'm living up here in Lübeck on the Baltic Sea, which is super cool in summer because when we have 45 degrees in Freiburg, which we did have, then it's nice and cozy with 30 here in Lübeck. So I love my weekends on the Baltic.
Yeah, that's amazing. I mean, that probably is. I mean, you were saying there's maybe two places, 2 cities, 2 points that are further apart within Germany, but you're pretty much at the 2 furthest locations. Yeah, but anyways, enough about where you live and everything like this. Do you want to describe your work a little bit and how you've gotten into neural implants?
So that is something which I'm more or less on every talk. I did tell everybody why the hell I'm in neuroengineering. And this was technically because of Star Wars at this time, episode 2. I'm that old that I know that when they had only a trilogy. So nowadays, episode 5 or so, this time it was episode 4. And I really like the idea of having the protagonist kind of losing. Well, I didn't like losing his hand, but I liked the replacement. This was very smart kind of. So they have this robotic hand. And at this time, I was a teenager. I was quite impressed, and I thought, I would like to do that. And then it turns out that making a robotic hand It's a mechanics problem, and technically you just need a lot of engineers to solve that problem. It's solved several times meanwhile. But what at this time I just did not get any idea of is how do you kind of control that thing just by your mind? So how do you get access to a artifact, to a artificial system somehow with your brain without using your hands? And that's something which absolutely fascinated me since I was 14. And so I kind of strategically planned my career that way. I started basic training on healthcare actually. So I was a nurse, you would call it, and for a little while, and then I studied physics. And after physics, I went to Caltech and I got my basics in biology and in implant stuff. So that was with the lab of Jim Bauer and Greg Kovacs in Stanford. They did have silicon probes as well. And with that knowledge, I went back to Germany and habilitated in computer science, software, signal processing. That's a big issue in the whole business here. And with all this knowledge together, I went now to Freiburg, where I was trying for quite some time within our cluster of excellence to get things progressed a little further on. That's something. This is more or less my career. That's the reason why I'm in this business. Is just fascination from my childhood times.
Yeah, that's really interesting. I've really only ever heard Americans talk about, Luke Skywalker and Star Wars, kind of motivating them, but it seems it made it across the ocean as well.
Oh, yeah. I mean, blockbuster, right? You couldn't avoid that at this time.
Definitely.
It even airs now and then again, so.
Yeah, exactly. It's good motivation. So now you're kind of focusing, you're working on longevity of brain implants, just general stimulation, kind of less contactless methods, near infrared monitoring of, neurons. And you kind of were talking about, actually, I don't know if you want to talk about this. You were kind of changing the direction of your studies and publications, everything like that. So do you want to talk a little bit about what you've been up to the last few years, and if you want to, the direction you're going?
Yeah. Well, I can. So here's the thing: when I came back from Caltech in 2000 something, I started in Europe the first silicon probe development. So we have now have the NeuroSeeker probes from Atlas, and you have other people who are doing the silicon probes in different ways. But at this time, I was setting up a European Union project, and we were producing silicon probes ourselves. And I thought at this time, okay, silicon is cool, it breaks. What else? Okay, so we went into metal probes. So we had multi-site there nowadays with different companies. They call U probes in one company and linear probes in the other company. Metal probes with microelectrodes on the shaft, unbreakable metal. That was cool, but then again, not small enough to what I wanted to have. And in particular, if you use that stuff for a longer period of time, you are facing gliosis, right? As everybody. So what is the next alternative? The next alternative was polyimide probes, flexible probes. I didn't have to make them myself, thankfully. There was one cooperation partner who did the first one in the Fraunhofer Institute, essentially. And then, thankfully, Stieglitz. That's Thomas' pet and pony, clearly. And he had those, and he was very helpful in providing us with some. And since then, we were trying to figure out what the hell is going on with gliosis. Can we reuse that? As everybody, we want to have a probe implanted which lasts forever, at least the lifetime of the human. And for that purpose, you need to overcome gliotic sheet. Well, you need to overcome deterioration in the brain, whatever the reason is. Be it technical deterioration, something breaks, or be it biological deterioration, it's completely encapsulated, no neuron close by, no spikes anymore. And this was kind of the path I was on. As it turns out, everybody's on that path meanwhile. And most people believe that it's solved based on the famous 8 micrometer carbon fiber, say, limit threshold to be below. This is, by the way, not quite true. There are reports out there of 15 micrometer wires, microwire bundles, which did last in monkeys for up to 7 years. So there are other methods too. You don't have to go for carbon fibers. You just have to go, and this is probably very, very true. You probably have to go with something which is small enough and which is flexible enough so it's bending with the tissue. Bending stiffness is the critical case. And that is something which is, in a way, sorry to say that is boring because everybody does it now. And as it turns out, we were looking a little beyond this plate, actually, where, well, GFAP staining, right, and ED1 or IBA staining and NUN staining and all this usually immunohistochemistry. We recently, well, a couple of years ago, we started with what happens with the genomics, with the transcriptome of the brain in this case. And this is something we are on it right now. I had two postdocs in my lab, which were excitedly learning about patch clamping and other stuff there as well. And then they went to another group, which is in neuro-oncology. So they were literally changing their fields to brain tumors. But with the knowledge they gained in the brain tumor business, and they have a lot of stuff going on in the transcriptomics, metabolomics business there, just to understand what the hell a brain tumor does. They came back into our area here, and we use that methods now to characterize flexible brain implants, like the Luan probes or like Thomas Stieglitz flex probes. And as it turns out, seems like nobody has done that. Well, people have done that. Erin Purcell had done that for neurons, what the transcriptomics of neurons is over time, but not for the rest of the cells. And we are working right now on a paper, which is due to be submitted next week or so, where we are really doing for up to 18 weeks transcriptomics, a lot of gene stuff. And we found a couple of, to me, interesting, perhaps even frightening results there, which I'm happy to share. It's just so surprising what's going on. That's all there is. If you look at the transcriptomics, not just the proteins.
Wow, that's really interesting. So you're kind of looking at the transcriptomics as something's being implanted in the glial sheath, kind of the transcriptomics of that. Okay.
What happens. So the method was actually we were implanting a flex probe, and we have the first time point at 4 hours. After 4 hours implantation, we are getting a punch of the area of the tissue around this implant, and that's kind of the first time point which we use then for transcriptomic analysis. The next one is after a week, another one is 2 weeks, 4 weeks, 8 weeks. The longest we have is 18 weeks. And if you look at the gene expression over time, you learn an awful lot what's actually going on in the cells which need to respond on the situation of this implant, even though it's a flex probe, where everybody believes right now this is the solution for all of us.
Interesting. And then actually, I want to go back to something that you had mentioned before, that we had talked about before we started recording. You were talking about the 15 micron limit. I in the podcast is what I was taught is the 8 micron limit. Below 8 microns, it's invisible to the body. But before the show started, you were saying, oh, it actually might be 1 micron. Do you want to explain this a little bit?
Yeah. Well, if you look at the stuff which is done by the Texas group, they have flexible structures in the size of 1 micron thickness and width electrode size. That's something in the range of 1 to 2 micron. And of course, the pictures that they produce telling us that the brain doesn't see them anymore, kind of is not reacting on. So 1 micron is roughly the size. I would say that is a good size. Still, you still need contacts and wires to the outside world. That means you are passing through a lot of tissue, which is not useful for you. I mean, literally, you're passing something through an area which may be even detrimental. I don't know. You're interested in the electrode on the very front. I mean, the best electrode, and Thomas Stieglitz said it so nicely in his podcast last. And he said, well, the best electrode, the best probe you want to have in the brain is one which is not there anymore. And this is actually the point. My feeling is the closest we can get with not being there anymore is actually nanoparticles. So you go with something which is below the 1 micron limit. And there are a couple of ideas out there which kind of propose nanoparticles to be used for both right into the brain, so stimulate the brain, and read out from the brain as well. This goes via a particular material which is called magnetoelectric. Or multiferroic. There are different terms for that, different purposes. And this magnetoelectric nanoparticles, they may be useful for stimulating via magnetization issue, and they may be useful for recording the same nanoparticles. So you have one not one nanoparticle. That's not sufficient. It's just too small. The technology doesn't last for that. But you have a couple of nanoparticles, a big bunch of them. And if you are smartly manipulating their magnetic environment, you could theoretically stimulate with their polarization, magnetoelectric ones, or the other way around. They could sense the electric field, local field potential sensing, and base, again, read out by magnetic, by their magnetization. So that's a plan we are right now trying to follow. And we started that plan by getting a new imaging system, which is called magnetic particle imaging, which uses nanoparticles, which uses superpower magnetic iron oxide nanoparticles to perform images in the bloodstream. And this is actually the core for the whole, or not the core, it's the, how you call it, linchpin, or the pivot point for the whole further project. We try to go in the direction of non-existing probes anymore, like by nanoparticles. That's the plan. That's the theory behind it.
Yeah, that's really cool. I mean, we were talking about it before we started recording, and it sounds very promising. And I mean, that's kind of the solution forward to the millions of electrodes that, or millions of neuronal connections that or access points or something that we want to achieve, or that we think that we need to achieve. Who knows if that's actually true? Maybe Utah Electrode had it correct. Maybe we only need 96 or 100 electrodes, and that's the maximum.
In the end, it just depends on the purpose, right? That's the point. You cannot say there is a maximum. There is a maximum for this particular purpose.
Yeah, exactly. So I kind of want to go back to the transcriptomics, genomics. What have you been finding out? You said you were, and again, you haven't published. You're going to be submitting, but it sounded like you were about to tell us like some big discoveries. So what can you share?
Well, there's no need for you to tell you big discoveries. You learn them sooner or later, anyways. There are a couple of things. I mean, when I started that business of longevity stuff, I did what everybody else did, immunohistochemistry. And in this context, I don't know, perhaps I'm naive and perhaps I'm stupid, that's possible. But my idea or my impression was that, hey, we have the acute phase of an implant after whatever 2 weeks or so, everything is cleaned up again. And after 2 weeks or after 3 weeks, we start with a chronic long-term response of the brain. And the difference you see is in the beginning, you have microglia activated based on ED1, ED1 or IBA staining. And then after 2 weeks, you just have astrocytes activated, GFAP staining. And that's what you see the difference there. As it turns, that's the first surprise to me. Perhaps, as I said, I'm naive or so. To me, the first surprise was that, well, you get GFAP activation from the very first day, literally from the very first hour. You get the formation of a kind of the innate immune response, the automated response of the body in the very first hour as well. This is the so-called complement formation, and complement is something which the body uses to destroy attackers by putting holes in them. Unfortunately, the complements as a protein, they are not putting holes in bacteria, which are somewhere you don't want to have them, but they put holes in neurons as well. So from the very first minute on, you are producing something which is very detrimental to your surroundings. Complement, GFAP is something which you did not want to have there at this time. And this is something we learned in the beginning. And in the end, after those 18 weeks, we learned that, yes, it takes at least those 18 weeks to go back to a relatively normal step wound-like transcriptomics in this environment. But if you look at the genes which are still active after those 18 weeks of flexible probe implants, those genes you find, unfortunately, in the oncogene database, in the cancer database. So I don't say that implants cause brain tumor, but there are genes active which you find in tumors. And this is something which, in my opinion, really needs a very thorough investigation before I would like to have something implanted in my brain, even if it's as easy as a LASIK surgery. So that's something which I learned. I'm not sure whether that is new to anybody else out there. There might be people out there who say, oh, we know that forever. Nobody was talking about that yet, at least not in the brain implant business. And that's something which we are shooting for now.
Fascinating. Yeah, I had never heard of this, and maybe the probes are too small to grow a larger tumor or something like this. Maybe it's extremely localized. But yeah, that is fascinating. I mean, it kind of makes sense because a lot of times, tumors are related to inflammation or hyper growth. A lot of body repairs and everything like this. So that could be yeah, maybe it is just a correlation, but. That's a very big question that's fascinating.
I wouldn't mind if it's only a correlation, but I want to be sure.
Yeah.
I mean, because this, if you want, we have a lot of projects right now in the glioblastoma brain tumor business, and I tell you, you don't want to have one single cell which is acting in the direction of a GBM. It's not a localized issue. It's something like one of those guys. As soon as they start acting up, and they're not stopped by the body, which is in the brain really tough to stop them, then you have another not even 2 years to live. Well, probably a little longer if it's only one cell because it takes till it develops. But the prognosis for brain tumor after it is detected is something like 15 months.
Wow.
You don't want to have that. And I would not really like to change a brain-machine interface to whatever entity against in 5 years down the road against the brain tumor, which is kind of terminating me within another 2 years. So that's something which I would little be frightened. And at least I'm not aware that anybody looked into this wider realm of the implant stuff. Where up till now, we all have been looking very close to what is the brain, what is the probe doing, what is the yield, how many neurons do I get, what neurons very recently, Aaron Purcell did that with what do the neurons react on the genomics basis. That makes completely sense to me. But there are microglia and there are astrocytes, there are oligodendrocytes. The brain is a lot more than just neurons. And it really makes sense to have a look, what the hell is going on there?
So things like deep brain stimulators, DBS, has been around for decades. I mean, wouldn't we have seen something like that in this, or is this more like a surface? Like, I guess where did you put those electrodes? Like deep in the brain structures or on the cortex?
No, we did cortex stuff. We did corticals. Because we needed to have a homogeneous tissue type. If we would go through corpus callosum, then the genes would mix just by the anatomy behind it. So we did that. And as I said, again, I do not say that this is really causing any type of brain tumor. Definitely not. I can't say that. Absolutely not. But the genes are there, and I can't kind of discuss them away. The genes are there. And this is something... Yes, then of course, better biologists than I will tell you that there's tons of oncogenes in the body turn on and off all the time and nothing happens, and that's actually their job to be having this behavior, blah 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 blah. Fine with me, but as soon as we found those genes in the oncogene database, I was a little surprised about their correlation to brain tumors.
Wow. Fascinating stuff. Yeah, I mean that's one of the biggest revelations I've actually had on the show. I think if it's true or not, yeah, I think this is really cool. Wow. So so you kind of started with it seems like you've had a lot of transitions in your career, and even now you seem to be you've it's almost like PhDs or something like this is what it seems like. You have these like 4 or 5 year sections, and then you kind of completely switch. Is that accurate, or what do you think?
No, not quite. I mean, the sections are more like 15 to 20 years.
15
actually.
To 20 years. Okay.
How
old are you?
How young do I look? No, I'm 40. I'm 54 actually.
54.
I'm 45. Sorry, I'm
45. Okay.
Well, what is it? I'm now getting 54.
54.
No discussion. I'm older than 50. That's kind of one of the disappointing things that I'm getting up and know that I'm older than 50. No, the thing is that it's just when Thomas Stiglitz said it very nicely. When he started this business in this field, he was more or less alone on the field. We started this at different labs with different kind of backgrounds. We started more or less at the same time, and we literally, it was a very, very lonely business at that time. I know that I recall that I gave my first job talk for a professorate in 2002, and it was a huge audience and a huge committee which was kind of assessing me, and they literally laughed at me when I told them about brain-machine interfaces and the use it might have for controlling artifacts and for communication in the future. 2002, I told them science fiction. And that is something which is, I mean, meanwhile, the field is getting literally crowded in a certain way. As Mark Engel said, we are still very friendly with each other. We are trying to get the field developed and not just having our own little fiefdoms and fighting against each other. So that is something which is still good, but you see a lot of things happening which you dreamt of yourself, and that is good, because even though I'm working quite hard, one single person, two persons, two groups could not come as far as the whole field is coming at this time, and this is really, really exciting. Wow. That's why I'm, by the way, quite happy about Neuralink. Because it's an industrial approach. That's why I'm happy about paradromics. It's an industrial approach, and that's literally the step which needs to be taken from the science part to the clinic. I'm looking for stuff which is going into patients, which is useful. It's not just proving I'm the first. I did this. I just don't care. As soon as it's proven good, it works. Now make it work for everybody at every time. That's the industrial type, and that is what I like at paradromics and Neuralink. What I'm not so sure about is what purpose. I mean, what is the goal behind the Neuralink game? They don't have a disease. They don't have anything particular which they would like to solve. It is. I don't want to be mean, but right now, to me, it sounds a little more like a rich man's toy, and that's something which does concern me. Because again, as other people said, if something goes wrong in this field, it will burn the ground for all of us.
Yeah, that's a really good point. So what did you tell the selection committee when you're becoming a professor? What was the purpose, or what was the, I guess, disease that you were trying to cure with that?
Oh, this was at this time playing communication and robotics. This was really the Luke Skywalker hand I was still dreaming of. And as it turns out, after a while, I did a little startup stuff. So I had my fingers in the one or the other and the third startup company. So I looked into what everybody is doing. If you really have a serious startup, what is the market? As it turns out, most people out there in the field, I mean, the number of hand amputees in Europe is minimal. It's a little more in the US with the many wars they are there.
You're welcome.
Yes, sorry. I mean, that's. Let's be honest, that's the reason why the DARPA put money on that field. There is a need, and they wanted to solve that, they kind of to satisfy that need, and it really makes perfect sense to me. So, but anyway, at this time when I looked at that, so the arm was still my dream, but it turns out this is not where the money is. Actually, the money is with diseases, and since 2005 or so, I'm working in Parkinson's disease, deep brain stimulation, and that is something we had recently. Couple of, I'm a physicist. I won't get any of my crazy ideas of stimulation, of parameters, of whatever into a patient soon, because in Europe we are lacking this IDE permit to test something out with patients. So everything we do here, I do on animals, on rat models. So we were publishing and we were working on rat model of Parkinson's disease, and we were trying to come up with, say, a test bed for crazy stimulation paradigms. Like Warren Grill has this one paradigm where he is a random sequence, essentially doing the same stimulation trick as this wonderful 130 hertz stimulation the clinical people are doing and enjoying. But I really like that. I mean, I particularly like that Warren showed that you don't need this nice 130 hertz. Something else might work too, but the question is still there. Why? How is it working? How is electrical stimulation working? It completely flabbergasts me. The more I learn about it, the less I understand how electrical stimulation is working. If you have just a bird's eye view, a very broad view, it's very easy to describe, right? You are activating channels here and blah, blah, blah. It's very simple. In detail, if you convolve that with the geometry of neurons in the brain, with the geometry of the brain itself, with the physiology, everything behind it, all of a sudden things start becoming a little more complicated. And I honestly have to say, I have a hard time believing that what we are doing right now is really more than just scratching the surface of something which can be a lot further be pushed down the road. And that's why we had this animal model of Parkinson's. It was a very useful model, or it is a very useful model, and is a disease which is very debilitating. The patients quality of life is the most important issue to them, and that's something which we were trying to help by coming up with new ideas, with new measurement methods, with something which even engineers can use. That's the reason why we were working the last couple of years in this field too.
Yeah, definitely. I mean, I also think that it's a really not low-lying fruit, but it's very it's amazing what the deep brain stimulators can do, and that's something that Elon Musk said was like essentially deep brain stimulation is like kicking the TV to get it to work again. And I think that's kind of we don't know how, like the frequency of the kick or the strength of the kick, but obviously there's much more going on behind the scenes, and like you said, we're just barely scratching the surface. But at least that's an actual use case versus you can tweet with your brain. I don't know.
Yeah, I mean, this is, but it brought me the idea that is there an alternative to electrical stimulation? And then we have nowadays, that's something I really like, that the focus ultrasound stuff. I'm not sure where that is leading, but at least there is a beginning there with an alternative, a true alternative. And then there is another alternative, which was the first time published in the 2007, 6, 7, somehow in this time, and which was infrared laser stimulation. And interestingly, not too much happened around it since then. I mean, a lot of stuff was written and stuff, but essentially it never found its way to the clinic. It never found a big use of that. And I think the reason was that it's surprisingly complicated. And that's something which we did the last years as well. I call it right now, I'm changing my field a little from the standard electrical stimulation to alternative and general stimulation, whatever the means is. And so we set up a laser stimulation, infrared laser stimulation system too, for peripheral nerve, not for the cortex. We tried cortex too. We did not get it working in the cortex. We did not see any positive results of laser stimulation in the cortex. In the periphery, in the sciatic nerve of the rat, we got it working very nicely. It was really cool. And the fun thing behind that is that we have a stimulation resolution, which is in the range of single axons. Well, at least of axon groups, put it this way. Whereas with electrical stimulation, you need to be very, very careful to really stimulate only a couple of axon directions. But in the laser stimulation, you could break it down to, well, the resolution was 25 microns on a sciatic nerve. And this is something which I really liked as well. We have a lot of experiments on that. That's something which the PhD student is writing up right now. He's defending soon. That's why he's not writing up as a paper, but he's defending soon. But it's one of those experiments, one of those projects I really liked the most. It was so much fun. 4 years of pure physics together with biology. That was just great.
Wow. Yeah, it seems all over, like, and that was kind of hard when I was like researching, kind of refreshing what you've been doing. Cause it's just like, it's kind of I guess it's an arc, it is kind of changing as things change and as, you're not the only one. Germany has hipsters. Yeah. Berlin is full of them. So you're maybe like the hipster neural implant. You're like, oh, this is too cool now. And I need to go to the more exotic, cool thing. Oh, you've never heard of it. Okay. Yeah.
I'm not sure whether I should feel good by being called a hipster now. I'm not sure whether that's a compliment.
I think it's good because it's kind of more trailblazing and I like that kind of stuff, not being satisfied with the status quo and kind of going towards
that is a clear point. I mean, I'm really not satisfied with the status quo. That's where I always try to find some new edges, and I go on the fringes of stuff. I mean, I go against the flow very often. I go particularly against the standard, say, catechism of our field, where people, hey, that's how it is, and then I ask, why is it really that? And as soon as you start thinking of different of those things, you start, well, is it really what you learn in your undergrad and grad school classes about what it is about? That is, head scratching is the stuff which starts me going on different projects.
I really like it. I mean, it's like I would consider almost like a German way. It's very direct, and I don't know. I think that's great. There's the one. Yeah, I can't remember his name. I think he's in California somewhere, and he writes a blog, and he's very like direct and very blunt about calling people out. But I think it's great. I think it's we need more of this kind of stuff. There's a reason I really like Germany. So as we're finishing up, Dr. Hofmann, is there anything that we didn't talk about that you wanted to mention?
No, I think I told you everything I know right now, and I don't want to spoil all the papers we are working on completely. I gave away a couple of the news we have in there. The only thing which is kind of something for your listeners is stay in the mainstream, but go on the fringes of it. Try not too hard to go against the flow, because this is very painful. You hurt your head very often and bump into rocks and stuff, but it really makes sense to flow somewhere on the fringes, in the area which was not very well described yet, just by asking, is it really reasonable what they are saying? Is the rationale behind it really something I can understand? It's very simple. Can I understand that? Does that sound like it's working? That's the question, which if you call that on your career, whenever you have the opportunity to do so, you will find new and crazy places. And then that's what I do. I try to go those crazy places and kind of find out whether they are green or not. That's something which is my philosophy. Have fun doing that. That's important.
Yeah, maybe even put that in the the first spot. Have fun doing it, and just keep learning. I mean, learning and discovering new things is a very rewarding thing, maybe the most rewarding thing. And and this is one of the ways you can do it, by constantly questioning yourself. May I say, being a good scientist.
I don't know what a good scientist is. Being a curious scientist. That's what I
curious scientist. Yeah.
But I have one more rewarding thing than just asking new questions and getting answers. The more rewarding thing to me is to see my students thrive and find their own way. I mean, I have many students, meanwhile, and a couple of them are professors now themselves, and that is extremely rewarding to see that somebody picked up something from our lab culture, our questions, and our direction, and that is even more fun to just have a paper out there. It's to see a family grow. That's big fun. That's the best fun, actually.
Wow. Yeah. I can imagine. I think that'd be really cool. Yeah. Well, one day. Well, Dr. Hofmann, thank you so much. This has been a pleasure. Always good to talk to you, and hopefully you'll make it over here to the US, or I'll come over to Germany.
Sure.
Maybe this year, 2021.
You know where we are. I show you my toys.
Yeah. Thank you.
Glad to see you.
Hope you enjoyed the show and were able to learn something new, bringing together different fields in novel ways. Until next time on the Neural Implant Podcast.